Yeah, so the units of a moment of inertia are kilogram meter squared, right? So this is our first clue, if we didn't know already, that basically the moment of inertia is a position squared weighted mass, basically. And so, so you can see right now so just in general, we know that inertia is going to be something like dm times f, right? Because we're weighting this by the position squared. And so an important thing to note here is that we're weighting it by the position squared. So this is nonlinear now. So this is going to depend on where we choose our coordinate system, which is something you guys have seen already, right? Of the moment of inertia of an object, it depends what axis you're rotating that object about, right? Like I said,
we're just now starting.
You're just now starting that?
I haven't even talked about moment of inertia yet.
Ah, okay, okay. That's probably why you guys are a little unclear about this. Okay, so this is probably a more in-depth study of moment of inertia, just to start you out, and then...
That's all right. The second years should know this already.
Okay. So as a start, let's pick our axis to be right here at the origin. And so we're talking about rotating it around the y-axis. So it's a little tough to draw onto the board, but you're talking if this is your rod, you're holding it at the end and you're rotating it about the very end. Does that make sense? So what we get, so again, we plug in, so our integral, we're talking about coming from the end of the rod here. So we're again going from 0 to L. We put in dm, which is m over L dx, and multiplied by x squared. And so why don't I give you guys a minute and see if you can figure out what this integral is. So does anybody have this?
ml squared over 3.
ml squared over 3. Okay, does everybody agree on that? That this is ml squared over 3? Okay, so just real quick to fill in the details. So we have the m over L as a constant. The integral of x squared dx is just x cubed over 3. And we're going from x equals 0 to x equals L. And so that's just m times L cubed over L times 3. And you cancel 1 power of L on each side. Okay, so this is pretty simple. So what happens now if instead of we want to rotate the rod about the end, we want to rotate the rod about its center? So if we want the moment of inertia about the center of the rod. So what's going to change? What part of this calculation is going to change now? The limits of integration, right. So what are the new limits of integration going to be?
Wherever that point is to L.
Okay, so I heard a 0 to L over 2, and what's...
Or wherever that point is. Oh, that's the center, right?
Yeah, so we're talking about this being the center of rotation now. Okay, so if this is the center of our rotation, if we rewrite the x-axis for this to be 0, then what's the left edge of the rod going to be?
Or negative L over 2.
Negative L over 2, right? So here, why don't we write this as IN, So down here, we have I center. Okay, so the left limit of integration is negative L over 2, and then what's the right limit of integration?
Over 2.
L over 2. Okay, and so what's the moment of inertia we get now?
Or why not just integrate from, or twice the interval from 0 to L over 2?
So, I'm sorry, what did you say?
Or why not just integrate, or do twice the integral from 0 to L over 2?
Okay, that would also work. Yeah, and I mean basically what he's saying is, so since you're weighting this by x squared is symmetric about the positive and negative x-axis. So instead of doing the integral from negative L over 2 to L over 2, since you have a function that's symmetric, you can just do the integral from 0 to L over 2 and then multiply that by 2. So for me, it's a little easier just to keep everything straight. And sometimes, again, if you have a non-uniform mass distribution, it might not be symmetric. And so for me, it's easier to just think about it, going from negative L over 2 to L over 2. But in this case, it's the same either way. And so what do you get this time for what the moment of inertia is? ml squared over 12. Okay, so this is again something that's a little funky and non-intuitive about moments of inertia. We have the same object, the same length, the same mass, but by choosing a different center of rotation, the moment of inertia is a factor of 4 smaller. And so this is something that's true of any object, and so it's important when you're thinking about moment of inertia to really keep track about what your center of rotation is. So a little bit closer to the real world, and also introduce, so the other thing that's going to happen when you start talking about moment of inertia is you're talking about rotational dynamics for the most part. And so most of the time when you're talking about rotational dynamics, you're talking about what type shaped objects?
Round.
Round. Okay, yeah, so you usually end up with round objects. Let's move on to something a little more physical that you're going to talk about rotating. And so let's say now that we have a two-dimensional disk. Okay? And so here's our disk. This disk has a radius big R, and it has a mass big M again. And we're talking about rotating this disk about its center, about what's not shown here, but the z-axis, basically. So, in this case, what are we weighting? One-dimensional case, it was just x squared, right? So now that we've moved on to 2 dimensions, what do we have to weight dm by?
X squared and y squared.
X squared and y squared, right? It's 2-dimensional, so we're weighting x squared plus y squared. And does that make sense? In that basically, you're weighting it along this axis and then along another orthogonal axis. Okay. So, in this case, another thing that's a little counterintuitive is, so in the original case, dm was a linear mass density, right? So it was a mass per unit length. And when we're talking about a 2